Hey everyone, Morgan here. So, on the last page of the lecture outline for acids and bases, I put in a couple things that we didn't treat anywhere else. Okay, so I just thought I'd give you a brief little introduction to them. One of them is a discussion of Kw. Now, let's remember that the reaction for Kw is 2H2O liquid to give us H3O plus aqueous and OH minus aqueous. Now, when we look at this set of Ks, with increasing temperature, the value is getting bigger. That means this is endothermic. Okay, that's an endothermic reaction. Okay, K increases with temperature. We could explain that with Le Chatelier's principle if you were so inclined. Okay? Now, what's the implication of that? Well, let's talk about a neutral solution at 50 degrees. Is the pH 7? The answer is no, it's not. Let's look at our icebox. All right, so there's our reaction. Do the icebox. Ignore the liquid water. 0, 0, x, 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 and x, right? X squared equals. Now, 50 degrees Celsius, that is 5.47 times 10 to the negative 14th. So x would equal 2.34 times 10 to the negative 7th. That's the H plus, also the OH minus, but that's not relevant at this point. So pH is the negative log of 2.34 times 10 to the negative 7th, which equals about 6.63. And you think, oh, so a neutral solution is acidic. No, it's neutral because the H plus and the OH minus have the same concentration. H plus equals OH minus. So the pH scale changes with temperature changing. Now, we almost always do everything at 25 degrees Celsius. Maybe only 3 times in my entire career have I seen a discussion about things at a different temperature. It doesn't come up very often. But I still want to point it out to you and have you ready to deal with pretty much anything that might come up. Okay? Now, a very brief look at the strength of acids and bases. Okay? And what we have to realize, this whole discussion is about how well does the anion hold on to a hydrogen ion. Okay? We know that Hickel, Hibber, and High are all strong acids. Okay? Strong. Actually increasing in strength that way. So this is the strongest. Okay? I have never personally had a bottle of HI. We have stocked HBr at one point, a very long time ago. Okay? Now, if HCl is a strong acid, it fully dissociates. So it doesn't hold on to its hydrogen ion very well. So even if I put a hydrogen ion back on it, it's just going to fall off again. That makes that a strong acid. So reasons for the increase in the strength, okay, are, sorry, I missed one down, larger radii, which means the hydrogen and the anion are not as close to each other. Hey, Coulomb's law again. And also, these are less electronegative, which means it's a weaker bond, stronger acid. Now, HF is a weak acid. A little bit of a conundrum there. Why? F minus is small, and it's very electronegative. And since it is small, the hydrogen can get up much closer, and Coulomb's law says we can have a stronger attraction there. Okay? More electronegative, stronger attraction. This is borderlining, going from covalent to polar covalent type, area. You get that nice, strong covalent bond characteristics in there. Now, here, these are just going to be, less strong bonds. That's it. The attraction's not as big. Now, what about for oxyacids? We know HCl is strong. No, but for the rest of these, this is the weakest, and this is increasing strength. Okay, so what's going on here? Well, electron density is getting pulled farther and farther away from the hydrogen because the oxygens are more electronegative. So we have a Cl here, double bonded to the oxygen. This is that one example I told you about that does exist for chlorine, for a halogen having double bonds. Okay, double bond oxygen down here. Sorry, folks, for some reason the recording seemed to have cut off, but the point that I was just trying to make was that with this structure, you have three very electronegative oxygens there, pulling electron density away from the hydrogen bonded to this oxygen, okay? And if you have less electron density there on the hydrogen and more over here to the left side of this molecule, you're going to get a weaker bond, and that hydrogen is going to leave more easily. You would see the exact same trend if this was, HBRO, HBRO2, HBRO3, etc., etc. Okay? All right. That's it for this lecture outline. Thanks for tuning in. This is Morgan, signing off.